Good evening. Today is problem solving session 5. Uh, today's session we would try to look at some of the sample problems from week 6 content, which will help you to solve the upcoming assignment for week 6, which is due on Wednesday. So we'll try to include a few questions from week 5 as well, because we have some basic Maxwell-Curl equations followed by this EM waves. So we will need to club these two content, okay, for today's discussion. So before going into the sample problems, first I would like to have a brief discussion of what was covered in the week 6. It is very a short summary of what is being covered in week 6. So week 6 starts with the electric magnetic field and the direction of propagation. So if you look at that, the very basic understanding is the electric and magnetic field lie in a plane perpendicular to the direction of wave propagation. So if you say the direction of wave propagation, say electric field is in x direction and magnetic field in y direction, so I can say x, y and z. So AX cross AY is AZ. So your direction of propagation is in the Z direction, whereas electric and magnetic field in the Y direction. It need not be always electric field is only in the X direction. It could have X and Y components. Similarly, the magnetic field can also have X and Y components. But the understanding is at any cost, the electric and magnetic field will be in a plane perpendicular to the direction of wave propagation. Okay. Now coming to what is a TEM wave. Okay. So this is a terminology which you come across in the week 6 content. So this is nothing but a transverse electromagnetic wave. So transverse EM wave. So the meaning of TEM wave is, so a wave in which the electric and magnetic field are perpendicular to each other. So that means electric field is perpendicular to magnetic field, and also they lie, that means the E and H both lie in a plane perpendicular to the direction of propagation. So maybe direction of propagation I can indicate with a unit vector k. So this electric and magnetic field will lie in a plane perpendicular to the direction of propagation of the wave. So such a wave is called as transverse electromagnetic wave. Okay. Now coming to what is polarization. So polarization, in a very short definition, we can say that it's the temporal evolution or time evolution of electric field at a given location in space. Okay. So in brief, very brief, I can say if the electric field is oriented in a particular direction, so it is the polarization is nothing but the orientation of that electric field. Say for example, if I say that electric field has an X component, okay, electric field has an X component and it has only an X component. If I say like that, in that case, it is a X polarized electric wave, that X polarized wave, or I can say it's a linearly polarized wave which is having the X direction. Okay, so I can say different types of polarization. Among them, one is linear polarization. Similarly, we also have a circular polarization and we also have elliptical polarization. So before going to the some of the questions on this, let's have a brief look at what is linear elliptical and circular polarization. This is very important to understand this concept of polarization. So let's start with linear. So in case of linear polarization, say for example, you have electric field and this electric field has x component and also y component. Assume that it has both components, Ex component and Ey component. And the angle between these components, Ex and Ey, okay? Angle between these components, if it is 0 degree or pi or 2 pi, so similarly plus or minus m pi, okay? So multiple of pi. So if the different phase difference between the Ex and Ey components are, if it is a multiple of pi or it is m pi, then we say that it is linearly polarized. Okay, so the magnitude of Ex, okay, so magnitude of Ex is Ex naught, or I can say simply magnitude of Ex and say magnitude of Ey. So this magnitudes can be any value. Okay. So there is an electric field in the x direction and the y direction. So there is component of electric field in x and y direction. But the phase between these two is either 0 or plus or minus m pi. In that case, we say that it is linearly polarized. Next is elliptical polarization. So how do you define an elliptical polarization? So this magnitude of Ex and Ey, Ex magnitude is equal to Ey magnitude, but the phase is not equal to 0. This is one condition, or we can also say elliptical whenever Ex magnitude is not equal to Ey magnitude and phi is equal to pi by 2. So this phi is nothing but the phase difference between Ex component and Ey component. So in both these cases, we call it as elliptical polarization. Now, when it becomes circular polarized, whenever phi is equal to pi by 2 or an odd multiple of pi by 2, and also this magnitude, Ex magnitude and Ey magnitude, both should be equal. So in this condition, we say that it is circularly polarized. Okay. Whenever we say elliptical or circular, we have two directions. It could be left hand circularly polarized or right hand circularly polarized. So this is purely based on the direction. So if it is left hand circularly polarization, because it is clockwise, and RHCP is anti-clockwise. So the direction of the time evolution of this electric field, if it is whether it is clockwise or anti-clockwise, based on that we say whether it is left hand polarized or right hand circularly polarized. We also say left hand elliptically polarized and right hand elliptically polarized. So the only condition is the magnitudes are equal, phi is equal to pi by 2 or odd multiple of pi by 2, it becomes circular. If these are not equal, if the magnitudes are not equal, then it becomes elliptical. Now, if the phase difference is 0 or multiple of pi, then it becomes linear. Okay, so that is a brief of polarization. So now we will move to some questions so that this concept of electromagnetic waves are clear. So let's see this question. First question is, consider the plane electromagnetic wave given by the expressions. So Ex is given, Ey is given, Ez is given. See, electric field has three components. Ex, Ey, Ez, whereas Ex and Ez goes to 0. So we have electric field only in the y direction. So I can say the polarization here is
Linear.
linear. And to make it more clear, it is in the y direction. So y
Yes.
polarized, I can say. Now coming to the question based on this. Say in this question, x is the position and t
Ma'am,
is
I
the
have
time.
a question.
Okay, yeah, please.
Ma'am, what I understand from polarization is towards,
Hmm.
it should be about something related to maybe a circle or elliptical, but linear, why do we call linear as polarization?
Okay, so if you have
Yeah.
gone through the lectures, you
Yes,
might
ma'am.
have seen a graph, something like this, probably. This is just to give you a to remind you about that. So, say if the electric field, as the time increases, time goes on, if the electric field is increasing linearly, and then again after some time it comes back, okay, and then
So this
again
is
in the opposite direction it increases, and then again it comes back. So, this graph is like a linear graph, right?
linear.
We call it as linear graph. So, that is why we say the resultant electric field is tracing a line with respect to
Okay,
time.
one single line. It is not
Yes,
circular or elliptical, but it is on a single line.
yes. So
Oh,
when we say linear, whenever the graph passes through origin, we say it is linear. Yeah. Okay. Now let's come back to the question. So straight away, this is a very simple question. Frequency of the wave. Can you please say what is the frequency of the wave based on this equation? Look at the equation and say what is the frequency. So if you remember,
the
this is,
standard form is omega 2 pi omega t.
yes, 2 pi
FT.
ft.
FT, sorry, ma'am.
Okay,
So 10 raised to power 14 is the frequency.
yes, exactly. So that will be the frequency. Now coming to wavelength. Very basic. If you know the frequency, wavelength is lambda equal to c by
C by
f.
F. Yes, ma'am.
So 3 into 10 power 8 by 10 power 14. Okay. So we
Yes.
get 3 into 10 power minus
Minus
6
6. Yes.
meters. Now, this is very interesting. Direction of propagation or motion of the wave. What is the
Why?
direction of propagation of the wave? Now you see, we are saying electric field. Okay, electric field is in y direction. Now, say this will be of the form a cos of omega t minus beta x. Okay, what you say, what what we say is if it is minus beta x, the wave is traveling in plus x direction. Okay,
Yes, ma'am.
the electric field is in y direction, magnetic field could be in another direction, but the wave propagates in the x direction. Okay, so from any wave equation, we can directly come to the direction of the propagation of the wave. So this is plus x.
Plus X direction.
Okay. Coming to the next question, this is very easy. Amplitude of electric field. Amplitude or magnitude, we can call it with any way. So amplitude is nothing but A. So here it is 2. Okay. Next question. What is the initial phase angle of the wave in radian? So initial phase angle. If you look at this, this is of the form A
Pi
cos
by 2.
omega t minus beta x plus phi. So initial phase is, yes, right, pi by
Pi
2.
by
So now the question is very easy. Polarization of the wave.
linear.
Exactly. Okay. So this was a comparatively easy question. Now let's move on to some a little little higher question based on the Maxwell
Ma'am, I
equation.
don't know the reason, but when you are doing it, everything becomes so easy and so simple. But when I am doing it, I somehow mix up things and I don't know where I get lost. I
Okay.
have to figure it out. I'll
Yeah,
this time
yeah.
I'll do this only. Whatever
Okay.
problem I face, I'll mail it to you with
Yeah, yeah.
screenshots.
Please do that.
Okay,
Please.
ma'am. Thank you, ma'am.
So, okay, coming to this question. So, electric and magnetic fields of a plane wave in a medium. Okay, it's not free space, it's a medium. So, please note that there is relative permittivity and relative permeability, although this is one. Okay, we don't have to worry about that. The electric field and magnetic fields are given. So directly it is understood that electric field has an X component and magnetic field has an Z component. Okay. So, and also the question is using Maxwell equations, find A and B. Okay, there is something A and B in these two equations. So we need to find those A and B, and we need to take the help of Maxwell equations. So last week I had discussed about the Maxwell equations. Four equations are there. So among them there are two curl equations. So I'll just write them, del cross E and del cross H. So these are the two curl equations which we need to solve this question. Okay. So let us write the other side of this. Del cross E is minus dou B by dou T, that is minus mu into dou H by dou T. And del cross H is j plus dou d by dou t. Okay. Or we can say this dou d by dou t becomes epsilon into dou e by dou t. Okay. So now let's see. So we have electric field and we have magnetic field. So how do we take the curl? So let us just write it down. I'll just make that clear. I, J, K. So these are the three directions. Dou by dou x, dou by dou y, and dou by dou z. And now see the last row should be Ex, Ey, and Ez. Okay. So here we have Ex, but we don't have Ey or Ez. So we say Ey and Ez is 0. So from this I can write del cross E. So what is del cross E? Minus j into dou ex by dou y. Okay. So that is your del cross. Sorry, this is dou z. I made a mistake here. Okay. So minus j into dou ex by dou z. Okay.
Yes, ma'am.
Next step is next is plus k into uh, dou dou ex by dou y. I hope this is fine. Yeah, there is a negative sign here. Okay. Now, if you look at this equation, dou ex by dou z. So this is our electric field, x component. If you take derivative with respect to z, can you say what is dou ex by dou z? There is no component that depends on
Zero.
z, so this
Yes, ma'am.
becomes 0. Now, dou ex by dou y we will have. Okay, let's
Because
find
those.
out that. Now, so this dou ex by dou ey, let us write it like, so k is simply a direction, so let us just avoid that. Dou ex by dou y, I can write 10, uh, okay, ex by ey when pi, cos becomes sine, okay, minus sine of 80 plus pi y, okay. So this is our dou ex by dou y. Now let us keep this aside. So this is our left hand side, and what is there on the right hand side? Let us equate it to that. So on the left hand side we have mu naught mu r. So mu can be written as mu naught mu r and dou h by dou t. Okay, so this is our h. If you take derivative with respect to t, so 10 into this becomes a by b, cos becomes minus sine at plus pi y. Okay, so this is dou h by dou t. Now equating these two. So this is our LHS and this is our RHS. So if you equate these two, what do we get? 10 cancels. What we get is mu r is basically 1. So mu naught A by B is equal to pi. Okay, I think this is fine. Now we can say A by B is equal to pi by mu naught. Okay, so this is one expression. Now, so in this we started out with del cross E, that is that curl equation. Now let's take the second equation, that is del cross H. So when we take del cross H, what happens? So let's try to write
Ma'am,
it.
can you please tell me what did we consider for K, LHS?
So K is basically a direction.
Okay, okay. It is only
So
telling us the direction.
it's only telling us the direction. Okay. So we are basically equating the magnitudes.
Yes, ma'am.
Okay, now del cross H, I can write IJK directions basically. Whenever we dou by dou x, dou by dou y, dou by dou z, and the third row will be Hx. Hx is 0, Hy is again 0, Hz we have a component. Okay, so Hz we will write as such. So I into dou Hz by dou y. Okay, j minus j into dou Hz by dou x, k into 0. Okay, now if you see dou Hz by dou x, there are no components depending on x, so this again becomes 0. So we have only dou Hz by dou y component. Okay, so let us see what is dou Hz by dou y. So if we take derivative with respect to y, it becomes 10 pi by b, and cos becomes sine with a negative sign, sine at plus pi y. Okay, so this becomes our left hand side. So this is LHS. Now coming to the right hand side. So this is our right hand side. Epsilon into dou E by dou T. So let us write here. Epsilon into dou E by dou T. Okay. So that becomes 10. So epsilon 0 into epsilon R into dou E by dou T will be 10. Whenever we take derivative with respect to time, 10A, and sine will be minus sine at plus pi y. Okay, and this is our right hand side. Okay, so this right hand side and this left hand side has to be equated. So once you equate those two, 10 and 10 gets cancelled. uh, a So that becomes epsilon 0 epsilon r A is equal to pi by B. Pi by B. Okay. So now AB is equal to pi by epsilon 0 epsilon r. So if you have so this was our first equation and this was our second equation. So once you know A by B and AB, it's very easy. You can find A and B.
Yes, ma'am.
I hope this is fine.
Yes, ma'am. I'm just if you can explain this part, which is right under the question where 13 is written. Epsilon into dou E by dou T is
Huh.
equal to this part, just once.
Okay. Epsilon into dou E by dou T. So what we say, epsilon is epsilon 0 into epsilon r into
And then we are
dou
derivating E with respect to
E
time.
with respect to time. So
Yes, ma'am.
when you take time derivative, A comes out. So
A
10A
sine 80
minus sine 80 plus pi by. So this becomes our
minus 9.
RHS.
Okay, okay.
Okay.
Minus sign I missed. Yes, ma'am. Okay.
Okay.
Done. Thank you, ma'am.
Okay. Going to the next. So this question is comparatively easy question. Let's have a look at in a non-magnetic medium, electric field is given. Okay. So 2 is the magnitude. From this equation now we need to try to understand each and every parameter. So 2 pi f. So this is f. So this is the magnitude of E. Okay, 2. Then beta. You see omega t minus beta x. So this is of the form a sine 2 pi ft minus beta x, or we can say omega t minus beta x. So beta is zero point 0.8. Now what is the question? Question is what is the relative permittivity? So there is a unknown medium. You need to tell what is the relative permittivity of that medium. So the first understanding is whenever a wave travels in a medium, the velocity changes. So when it is in free space, the velocity is c. But when it is in a medium, it's not c. So that velocity will depend upon the relative permittivity of that medium. Okay, so that is our main understanding here. So whenever the wave travels from free space to a medium, what happens? The C will become C by root of epsilon r. So this is the main understanding which you should have. Second thing, to, to find the phase velocity or velocity, there is another formula that is omega by beta. So we know what is omega and beta from the electric field equation of the wave. So then it is easy for you to calculate what is Vp. And the same Vp can be equated to C by root of epsilon r, from which you can calculate epsilon r. Okay, so let's start doing that. Vp is equal to omega by beta. 2 pi into 10 power 7 divided by beta is zero point 0.8. So this becomes 7.85 into 10 power 7 meter per second. So this has to be equated to what? C by root of epsilon r. And we already know what is C. C is 3 into 10 power 8. And this is 7.85 into 10 power 7. So now epsilon r can be calculated. So that is nothing but C by V the whole square. Okay. So 3 into 10 power 8 by 7.85 into 10 power 7. So that whole square. So this finally comes out to be 30 by 7.85 square of that. So that will be 14.6. So that is our relative permittivity. Now, coming to the second part of the question, what is the characteristic impedance? See, this is not free space, this is a medium. So, what is the characteristic impedance of a free space? that we call it as eta naught. Eta naught is root of mu naught by epsilon naught, and you already know the value. It is either 120 pi, or we call it as 377 ohm. The value is 377 ohm. Now when it becomes a medium, what is the difference? It
Mu
becomes
naught mu
eta.
r by epsilon naught
Excellent.
epsilon r.
Yes, exactly. So it is nothing but eta naught into mu r by epsilon r. Okay. So assuming that mu r is 1, okay, then we can say epsilon r we already calculated. You can just find out eta naught is basically 120 pi by root of 14.6. So this comes out to be 98.66 ohm. So this will be the characteristic impedance of the medium. Okay. Now the third part, time averaged power in watt per meter square. So this is an interesting question. We know that Poynting vector P is E cross H. Okay. To write H in terms of E, what do we do? E by H is eta. Okay. So if I want to write H, I can write E by eta. So I can write mod E square by eta for the Poynting vector. Okay. So time averaged power is nothing but E square by, so that means mod E square by 2 times eta. The reason is, so this say we say RMS value and maximum value. Okay. So time averaged power will be, so RMS, say if you want to write ERMS will be E max by root 2. Okay. Similarly, HRMS will be what? H max by root 2. Okay. So if you want to multiply these two, then that becomes 1 by 2. So mod E square by 2 times eta. Okay. So then mod E square by 2 times eta. What is mod E? 2. So 2 square 4. 4 by 2 into eta is the medium impedance 98.66. So this comes out to be the averaged time averaged power. Value will be 0.0203 watt per meter square. Okay. You can try calculating.
Ma'am, please explain this P average. Why we get 2 in denominator?
So you see RMS value and maximum value. So you know this fundamental relation. RMS is
Oh,
nothing
okay,
but
okay,
E
okay,
max
okay.
by root 2.
Okay.
So when you take the multiplication of that root 2, that
हाँ हाँ
becomes 2.
हाँ. Sure.
Okay. Okay, now we'll move on to another question. Okay, this is a comparatively easy question to try. So let us see one by one. So there is a slab of perfect dielectric material. So epsilon r is given to you, 2, and that is placed in a microwave oven. And the oven produces an electric field as well as a magnetic field. Okay. Assume that the electric field intensity is uniform in space and sinusoidal in time, and it is in the direction perpendicular to the surface of the slab. Microwave oven operates at a frequency of 2.45 GHz and produces an electric field intensity with amplitude 500. So, amplitude of the electric field, that is 500 volt per meter inside the dielectric. Calculate the displacement current density. So, this term is very important. JD, displacement current density, is nothing but dou D by dou T. And this will be written as D is epsilon r. So epsilon 0 into epsilon r dou E by dou T. Okay. Now, so if you have the electric field take the derivative of that and multiply by epsilon 0 epsilon r, you will get the displacement current density. Okay, now let us start from the electric field. Okay, say for example, electric field, let me write it like this: E naught. So E naught is the magnitude, E naught sine omega t. Why we write like that? It is already given in the question. Electric field intensity is uniform, so that means E naught is constant, and then it is sinusoidal in time. Okay, so sine omega t. Now, so I can write epsilon 0 epsilon r. Now, dou E by dou t. What happens? Dou E by dou t, omega E
Cos omega.
naught cos omega t. Okay, so that is our JD. Okay, now do we know epsilon r? Yes, we know that it is 2. Do we know E naught value? Yes, we know that 500 volt per meter. And do we know omega value? Yes, we know that oven operates at 2.45 gigahertz. So 2 pi f, 2.45 into 10 power 9. Now cos omega t, inside that we can write, okay, omega t, that is fine. Now when we say, so the question is about the displacement current density. So if you want to take JD, so that will be 8.85 into 10 power minus 12 into 2 into 2 pi into 2.45 into 10 power 9 into 500, that much cos of omega t. So how do I write? 2 pi into, again 2 pi into 2.45, so that will be 4.9 into 10 power 9 t. Okay, so if you multiply all this, you are going to get 136.3. So 136.3 cos of 4.9 into 10 power 9 t. So this will be the displacement current density. And always current density unit will be, so current per unit area. So ampere per meter square. Okay.
Ma'am, I
I
just missed the initial part where
mm.
we put JD and dou D by dou T and this epsilon naught. Please explain that
So
once.
JD, I
Hmm.
hope you remember
Hmm.
the Maxwell equation when I told that
Yes, ma'am.
J plus dou D by dou T. Okay. So this is the understanding. So this is your conduction current and this is your displacement current. So dou D by dou T is your current, that means your displacement current density. Okay. So this D is what? Epsilon into E. Okay. This is the fundamental relationship. So instead of epsilon, I should write epsilon 0, epsilon r because it is a medium. So into dou E by dou T. Here what you do is you take the derivative of the E with respect to time.
No, further I understood. What I want to understand is JD is equal to dou D by dou T
Hmm.
because
Oh, okay, okay. So you are saying why JD is dou D by dou T.
yes, ma'am.
Oh, okay, okay. So I think then I have to go back to the curl equations where we discussed this curl equations. I don't have the previous
I
lectures.
have, ma'am. I've written it.
So if you
Please tell.
remember, I
Yes,
told that J plus dou D by dou T. So this was a modified Ampere's law, if you remember.
yes, ma'am.
So Ampere's law was only this much, and this term was added to Ampere's law by Maxwell. So Maxwell has modified this equation, wherein this J is basically sigma into E. That means this is the conductivity, and this is the electric field, and this is our displacement current density. So when we say
Epsilon E.
yeah, so just remember one thing. There are conductors, there are dielectrics.
Yes, ma'am.
So in conductors, the conduction current dominates, whereas in a dielectric, the displacement current dominates. So that is a basic understanding
So
of
the conduction current is J and
huh.
okay.
And this is JC. Some textbooks will say that this is JC and this is JD. And if you refer to some of the textbooks, they'll explain with the help of a capacitor. Say, capacitor is basically two conducting plates separated by a dielectric in between. Okay. So, if you remember, we say the displacement current in a capacitor with the same explanation of JD. So I think I have one more question which will explain it better. Uh, we'll move on to that, and I can explain the capacitor part there.
Okay, ma'am.
Okay, okay. We are skipping one question. Let us move to this first and then come back. Okay. You see, this is a parallel plate capacitor. Okay, parallel plate capacitor with a plate area, sorry, the plate area is 5 centimeter square, and the plate separation, that means the separation or the distance between the plates D is 3 millimeters. Okay, and this so this onto this capacitor we are applying a sinusoidal voltage. Okay, and that is 50 sine 10 power 3 t. Okay, so we are applying a sinusoidal voltage to this capacitor plates, the plates of this capacitor. Calculate the displacement current assuming epsilon is equal to 2 epsilon naught. Okay, so displacement current needs to be calculated here. So how do we do that?
D is equal to epsilon E.
Yes, JD, again, JD is the displacement current density. Let us keep that in mind. JD is dou D by dou T, and this is epsilon into dou E by dou T. Okay, now let us move to the next step. What is electric field? Okay, in case of a capacitor, what is electric field? Electric field is voltage applied divided by the distance between the plates. So, so voltage applied divided by distance between the plates. So distance between the plates is a constant number. So epsilon by D into dou V by dou T. What is applied voltage to the capacitor? It is a sinusoidally varying voltage. So I have to write dou V by dou T. Okay. Now epsilon by D. Now this is current, displacement current density. So I told it is in ampere per meter square. So how do we find displacement current from that? Multiplied by area. Okay. So multiply JD with area, you will get current, displacement current. So epsilon A by D into dou V. So let us write dV because it's only one dV by dt. Okay. Now look at this. What does it mean? What is epsilon A by D? Epsilon A by D, if you remember, that is the capacitance. Okay. And so C, I can write it as C dV by dt. See, this is a very basic
Mm,
relationship,
yes.
capacitance, current of capacitance. So C into dV by dt. So wherein C is nothing but the epsilon A by D. So now I hope you this is clear to you. This whole picture is clear to you. Now,
Yes.
what is the question asked here is to calculate ID. Okay. To do that, what do we do? Epsilon is epsilon 0 into epsilon r. Here it is mentioned that epsilon is 2 times epsilon 0. So 2 times epsilon 0 into plate area is 5. So let us make it as 5 into 10 power minus 4. And D, plate separation is 3 millimeter, 3 into 10 power minus 3. Now dV by dt, see this is voltage. So what is dV by dt?
50
50
into 10
into
raised to the power 3 into cos 10 raised to the power 3t.
yes, exactly. That's all. Epsilon 0, you substitute the value and just simplify the whole thing. You must be getting the final answer. Say it is 147.4 cos of 10 power 3 t. And this current, so there is a multiplication factor, so nano amperes. So it whatever you get should be in 10 power minus 9. So it's nano
Okay.
amperes. Okay. Now we'll go back to that question which we skipped. Okay. Okay. Assume that sea water has mu equal to mu naught and epsilon equal to 81 times epsilon naught and conductivity. So you know that seawater is conducting. So conductivity is 20 Siemens per meter. Determine the frequency at which the conduction current density is 10 times the displacement current density. So there are two terms, conduction current density JC, displacement current density JD. So the condition here is JC is 10 times JD. So when will this happen? You need to find the frequency at which this happens. Okay. So JC is equal to 10 times JD. Now let us see what is JC and what is JD, and then we can come to this question. So as I told before while discussing the Maxwell equation, JC is sigma into E. And what is JD? JD is dou D by dou T. Okay. So if you know these two fundamental relation, let us write it. Say electric field, suppose that it is sinusoidally varying or cosine, or you can write however you want. So sigma Em cos omega t. Okay, let us write E like this. Now let me write JD. So how do we write JD? I need to write it like epsilon dou E by dou T. So I'll write it like dou E by dou T. So E is Em cos omega t. So epsilon into omega Em sin omega t. There will be a negative sign. There will be a negative sign. Now, if we want, we can write it as omega epsilon Em cos of omega t plus pi by 2. Okay, cos 90 plus theta is minus sin theta. Okay, so now if you compare JC and JD, let us take a ratio. Okay, JC to JD. If I take a ratio, the magnitudes, okay, let me tell you the magnitudes. JC to JD, if I take the ratio, sigma into Em divided by omega epsilon into Em. So I am taking only the ratio of the magnitudes. Em get cancelled and we get sigma by omega epsilon. So this is the basic understanding what is the ratio of the magnitudes of conduction to displacement current, that is sigma by omega epsilon. And in the question it is being
It is given
mentioned that
as 10.
10 exactly. So
Mm.
equate it to 10. For that sigma is given, you
20.
know epsilon, you will find out omega. Okay, so sigma is 20 by omega is 2 pi f into epsilon is 81 times epsilon naught. which is 8.85 into 10 power minus 12, which is equal to 10, and you will find out f from this. Okay, so
Yes.
once you solve, you can try solving, you must be getting 0.44 gigahertz. So the basic understanding is the fundamental relationship JC is sigma E, JD is dou D by dou T. So if you
Yes.
know that, just take the ratio, equate it to 10. That's all. Say this. So let us, since we come across this terminology, I think I should discuss. I should just discuss this part. Transition frequency. So transition frequency is the frequency at which JC becomes equal to JD. That means the conduction current density equal to displacement current density. That frequency will be called as transition frequency. And there is one important parameter. Say now we took the ratio like JC by JD. So when we took the ratio, we got it as sigma by omega epsilon. Okay, so let us have a look at that ratio once again. JC by JD is sigma by omega epsilon. So if it is a good conductor, if it is a good conductor, sigma by omega epsilon will be very, very greater than 1. Very understanding, because sigma, that is conductivity. So if it's a good conductor, sigma by omega epsilon will be very large. Okay. Whereas, so this is a good conductor. Whereas, whenever sigma by omega epsilon is very, very small or very, very less than 1, we say that it is a good dielectric. Okay. From this, again, I'll come back to my first point. If it is a good conductor, the conduction current density dominates. Similarly, if it's a good dielectric, the displacement current density dominates. So, just wanted to connect this idea. So, similar. So, we have discussed these 2 points. So, we'll discuss as and when the questions come. Okay. Okay. Let's move on to the next question. So here it's mentioned in a non-magnetic material with mu r1, dielectric constant epsilon r is 4. The electric field is given by E of t 20 sine 10 power 8 t minus beta z y. So electric field has a y component. Calculate the propagation constant beta and magnetic field h of t. Okay. So let's see. I think this question we can uh, take a close look and try. So epsilon r is given 4. Electric field is given 20 sine 10 power 8 t minus beta z into y cap. Okay. Here it's omega t minus beta z. Say this is modulus of or magnitude of E sine of. Okay. So what is the understanding from here? Magnitude of E is 20. Angular frequency is 10 power 8. So these and also electric field has a Y component. Okay. Now we need to calculate the propagation constant beta. Beta is omega root of mu epsilon. This is a very important relationship. So omega is directly understood from the equation. It is 10 power 8 into root of mu is mu naught mu r. Because mu r is 1, I'll write mu naught. Epsilon naught epsilon r. So epsilon naught into epsilon r is 4. Now 10 power 8 into 2 into root of mu naught epsilon naught. Okay. Uh, this is a uh, all of everybody knows this. C is 1 by root of mu naught epsilon naught. That way I can just simplify this. So 10 power 8 into 2 divided by C I can give. So 3 into C value is 3 into 10 power 8. So this will be 2 by 3. So your beta is 2 by 3. Okay. Now, so we calculated the propagation constant. So once you know the propagation constant, uh, we need to calculate what? The magnetic field. So we know electric field. From electric field, how do you calculate the magnetic field? So you need to use the Maxwell equation. So what is that Maxwell equation to be used? Del cross E is equal to minus dou B by dou T. Okay. Or I can write minus mu into dou H by dou T. Okay. Now, always I'll write it in time domain form. I would like to also introduce the frequency domain form. So, how do we write in frequency domain form? Del cross E, I can write it as such, minus mu. Whenever there is a dou by dou T, the rule is replace it by j omega. Okay, j omega h. So minus j omega mu h. So that is the frequency domain equation. Okay. Now, what do we need to calculate? We need to calculate h. Do we know E? Yes, we know E. So, H is equal to del cross E divided by minus j omega mu. So, we know del cross, how to calculate del cross E. So, I'll just write it here. Del cross E I j k dou by dou x, dou by dou y, dou by dou z, and electric field x component 0. There is a y component, but z component is 0. Okay. So this will be I into dou ey by dou z. Okay. Dou ey by dou z. So I can write it here. What is del cross E? So I'll write it here directly. Del cross E is minus j into minus, oh sorry, I into minus dou ey by dou z. And the last component dou
K
ey by
component.
dou x becomes 0. So divided by minus j omega mu. Okay. Now,
Ma'am, the reason why dou E by dou X, which is in K direction, is zero is because there is no component.
if you see dou ey by dou x, there is, in the electric field there is no component depending on x,
Okay.
t and z, only t and z. Okay, so this is dou Ey by dou Z. So to get that, what do we do? Minus Ey by Ez. So we have to take derivative with respect to Ez. So minus beta will come out. Minus beta into 20. Sign becomes cos. Cos of 10 power 8t minus beta Z. Okay. So from this, we can understand that, so minus j omega mu. So this will be minus minus plus beta, 20 beta. So beta we already calculated, 20 into 2 by 3 cos term. So basically, this is a time domain equation. This cos of this can be written as e raised to minus j beta z. In frequency domain form you can write, divided by omega into mu. Omega into mu. And one thing to remember, if you see there is a direction I here. Uh, I can call it as either I, or I can also say that it is x direction. So here the electric field is in y direction and the magnetic field is in x direction. So that is something which we can understand from while solving this del cross E. So there is a relevance for the direction when it is needed to know. Okay. So electric field is in x direction. So if you solve this, you will get the final answer. Omega is 10 power, what is omega here? 10 power 8. Okay. So this is 10 power 8 and mu is uh, mu naught, 4 pi into 10 power minus 7. So you can solve this. So once you solve, you get the magnetic field. And the basic understanding is that magnetic field is in the x direction. I hope this is clear.
Yes, ma'am.
Okay. So the next question, uh, this question is on polarization. So understanding of polarization. So there are two linearly polarized vector fields. So if you say this is F1, one is F1 vector and other is F2 vector. Okay. You can see that both of them are like sinusoidally varying thing. Okay. Sinusoidally time varying and linearly polarized vector fields. So linearly polarized vector fields. And so, and C. So in this, there is a constant term C, which is unknown to you. The first part of the question is determine the polarization of the vector F1 plus F2 for C is equal to 2. Okay. So first we need to uh, just substitute the value of C and see that what is F1 plus F2 and what is the polarization of that vector. Okay. So let us do it one by one steps. So whenever C is equal to 2, what is F1? F1 is equal to uh, 2ax plus 2ay plus az into cos omega t. And F2 is 2ax plus ay minus 2az, okay, into sine omega t. Now F1 plus F2, okay. So there are two vector fields. Take the addition of those two vectors. So when we take addition of two vectors, F1 plus F2, magnitude of this f1 plus f2. So basically, so let me simplify this. So the first term is like f1 is equal to mod f1 cos omega t, and the second term f2 is like mod f2 sin omega t. Okay, so what will be f1 plus f2? F1 plus f2 is like there are two terms. So how do we write it? Magnitude will be like f1 cos omega t the whole square plus f2 sin omega t the whole square plus 2 f1 f2 sin omega t cos omega t. Okay, so this is the resultant. So f1 plus f2, and we take the magnitude of that. So this under square root is for the whole term. Now, if the resultant has to be, so we need first we need to understand what happens when c is equal to 2. So in that case, we can find out the magnitude of f1 and f2 separately. Let's see, modulus of f1 will be what? Root of 4 plus 4 plus 1. What is magnitude of f2? Root of 4 plus 1 plus 4. So this is 3. Again, this is also 3. So what is the understanding? Mod f1 is equal to mod f2. Okay. Both are equal to 3. Now, what is f1 dot f2? f1 dot f2, it is not equal to 0. And f1 and f2 are not. Now, so this, what is dot product, you already know. A dot product is a dot b is ab cos theta. So f1 f2 cos theta is not equal to 0. So if it is not equal to 0, then we know that f1 and f2 are not in the perpendicular direction. Okay, so we say that this vector f1 plus vector f2 is elliptically polarized. How do we say elliptically polarization? Because these two magnitudes are same, but angle is not 90 degree. So the basic understanding of elliptical polarization, there are two cases. Either okay, basic of elliptical polarization, either the magnitude should be equal and phi not equal to 0, or magnitudes are not equal and phi is equal to pi by 2. Okay, so in that it is satisfying the condition for, so our question f1 plus f2 is satisfying the condition for elliptical polarization. Now the second part, find the value of C for which f1 plus f2 is a circularly polarized wave. So if it has to be circularly polarized, then f1 dot f2 should be 0. Okay. If it has to be circularly polarized, the angle between those two should be pi by 2. Okay. So how do we write that? f1 dot f2 should be 0. When that will happen? You see, if I take f1 dot f2, what happens? 2 into 2, 4 plus 2 into 1. So 2 into 2, 4 plus 2 into 1, 2. 1 into minus 2. Okay, 2 minus 2, it is 0. So this is 4. So f1 dot f2 is 4. It's not equal to 0 here. But when it will become 0? For that, what should be C? Okay. For that, if you take C value as minus 2, C value as minus 2, say this is minus 2. So minus 2 into minus 2. So I am taking f1 dot f2. Minus 2 into minus 2. That becomes 4. Again minus 2 into 1. That becomes minus 2. Then 1 into minus 2. Again that becomes minus 2. So f1 dot f2 becomes 0. Now the second condition. Magnitude of f1 and f2, is it equal to 3? So magnitude of f1 in this case will be 2 square 4 plus 4 plus 1. So root 9, that is equal to 3. Again magnitude of f2, 2 square 4 plus 1 plus 4, again root 9, it is 3. So magnitudes are equal. The second condition is f1 dot f2 is 0. Then it becomes a circularly polarized wave. So the value of C for which it becomes circularly polarized, that is C is equal to minus 2. Is this question clear? Any clarifications needed?
No, ma'am, it is clear, but it is a little complicated kind of question.
Okay, okay. Maybe you can watch the recording.
I'll go through it again, but it is clear.
Yeah, okay, okay, okay. Now let's move on to uh, ah, so this question, I wanted to introduce a few things which was discussed in week 6. One is loss tangent. Another thing is complex permittivity. Okay. So I wanted to introduce these two terms by discussing these question. So what is complex permittivity? So we always say relative permittivity, uh, but there is something called as complex permittivity. What is that complex permittivity, that we need to understand first thing. Okay, so when we say in a conductive medium, uh, so so in a conductive medium, as I said before, there is a conduction current density, and also there is a displacement current. So it's not a very good conductor, it's a conducting medium. So in such cases, both the currents are present, conduction current and displacement current. So I can write the Maxwell equation like this. Del cross H is equal to JC plus JD. I'll write JC as sigma into E, and I'll write JD as dou D by dou T. But instead of dou by dou T, I'll write J omega D. So instead of D, I'll write epsilon 0, epsilon R E. Okay. Uh, Now take out E you can take out sigma plus j omega epsilon naught epsilon r into E. Okay. Now let us take the next step. Take j omega epsilon naught. If you take out, what will happen? Sigma by j omega epsilon plus epsilon r into E. Okay. 1 by j is minus j. Okay. So j omega epsilon naught into, so let me take this term first, epsilon r. 1 by j is minus j sigma by omega epsilon naught into E. Okay. Now see this. This is of the form j omega epsilon naught epsilon rc into E. Okay. So what is epsilon RC? This is. So the complex permittivity. So complex permittivity means The permittivity has a real component and an imaginary component. So this is epsilon r is the real, and what is the imaginary part? Sigma by omega epsilon naught. That is the imaginary part. Now that imaginary part, okay, that imaginary part is also called as loss tangent. Okay, so the loss tangent is generally denoted like tan delta, loss tangent. Okay, and this tan delta is sigma by omega epsilon naught. So this is nothing but the imaginary part of the complex permittivity. Okay, so this is just a brief of what happened in during the video lectures by professor. So you can go through the lectures in detail. So I just wanted to take out this
And
content.
why do we call it loss?
Okay, so let me come to that. Okay, let me. Okay,
Just
as
this
I
is the
told,
imaginary part of the
relative permittivity,
ah.
exactly. So if you say dielectric, uh, so we can say a the best dielectric will have sigma by epsilon omega epsilon naught very less than 1. Okay, uh, so dielectric, so you say, how do I say that, to explain that in a better way? Uh, okay, let's take this way. Uh, so you have a good conductor. So in a good conductor, sigma is high, right? So in a good conductor, sigma is going to be high. So what will be tan delta? Tan delta is going to be high for in that case. But if it is a good dielectric, sigma is going to be small and tan delta is going to be small. Okay. So what is loss tangent? So it's kind of compromise between whether it is a good dielectric or whether it is a good conductor. So if it has a smaller loss tangent, then it becomes a good dielectric. Hope that makes sense. So when I say good dielectric, there is also one thing, the attenuation. Say if sigma is high, what will happen? Attenuation, alpha. Okay, alpha will also be high. Okay, at the same time, if sigma is small, alpha will also be small. The attenuation will be less. So, if I say a dielectric has a smaller loss tangent, it means that it is uh, conducting better. Does that make sense?
Yes, ma'am. Less
Okay.
loss, more conduction.
Yes, exactly. So, generally, we say for any dielectric, if you tell that it has so and so loss tangent, that is an indication of how good the
It
dielectric is,
conducts.
or how good that is a conducting that way. Okay, how good the transmission is, I can say in that way also.
Hmm.
Okay. Okay, now let us come back to the question.
So the value
Loss
of loss
tangent.
tangent should be low for
Yeah,
a good system,
for a good dielectric.
for a good dielectric, for a good conduction,
Yeah.
for good transmission. Yes.
Okay. Now, loss tangent. Coming to loss tangent, I already told the equation sigma by omega epsilon naught. Now, the what is given is intrinsic impedance, so eta. What is eta? So, if you look at this, this is like a polar form. So this gives an indication that if you take the if you convert it to rectangular, this becomes something like a plus jb, which has an real part and a imaginary part. So 240 angle 30 means 240 is the magnitude and this angle, okay. So this angle I can write theta is half of tan inverse sigma by omega epsilon naught epsilon. So these equations are already discussed in the lectures. I don't want to go into those details. So this is the angle theta, okay, of the intrinsic impedance. So intrinsic impedance, this is intrinsic impedance. One is magnitude, the other part is the angle. That angle is half of tan inverse sigma by omega epsilon. Okay, so this is 30° from your understanding. So that is half tan inverse of sigma by omega epsilon. So once you know this, the easy way is 2 into 30 tan of will be sigma by omega epsilon. Okay. So what is Law's tangent? Tan 60. Tan 60. So tan 60 is root 3. Okay. Law's tangent we also call it as tan delta. Law's tangent or tan delta is tan 60, which is root 3. Okay. So first part is done. Now coming to second part, dielectric constant. So remember, dielectric constant is epsilon r and complex permittivity is, if you remember, epsilon r c. So it has a real and the imaginary part. Now, if you look at the magnitude of the impedance, what is magnitude? Eta root of uh, mu naught mu r by epsilon r. Okay, so that is 240. Okay, eta is 120 pi. The root of mu naught by epsilon naught, we can write it as 120 pi into root of mu r by epsilon r. And we know the magnitude is 240. 240 is equal to 120 pi into root of mu r, we take it as 1 generally, and epsilon r is something which you need to find. So this is a direct equation, you can find out epsilon r from this. Okay, now coming to complex permittivity, epsilon RC. What is epsilon RC? Epsilon R minus J sigma by omega epsilon. So, sigma by omega epsilon. So, just substituting all the values. Sigma by omega epsilon is nothing but this Law's tangent. We already found sigma by omega epsilon. So, and also here in the second part you calculated epsilon r. So, take that both, you get the complex permittivity. Now, coming to the last part, that is the attenuation constant. So, how do we calculate alpha attenuation constant? So, for that there is a direct relationship, omega by c into root of mu r epsilon r by 2 into square root of 1 plus sigma by omega epsilon the whole square minus 1 Okay, so this relationship -1. Okay, so if you solve, you will get the attenuation constant. All the terms are known to you. Sigma by omega epsilon, always remember that is a loss tangent which you found in the first part. And rest are all non-values. You can get the final answer would be 0.0164 Napier per meter. Okay.
Yes, ma'am.
Mm, now I think we can discuss this question rather than discussing this. Okay. So this gives a better idea to solve some questions in the assignment. Uh, okay. So if you see, there are two equations written there. Electric field equation and magnetic field equation. So from that, okay, I think we can discuss this in the next week because this includes some concepts from the week 7 also. Okay.
Okay,
Uh,
ma'am.
okay, okay, let's have a look at this question. For copper, mu is given, okay, and epsilon is equal to epsilon naught, okay, and sigma is given. Sigma is the conductivity. So these are all in the case of copper. Assuming these are frequency independent, find the range of EM spectrum for which copper is a good conductor. So, uh, as I said before, what decides whether it's a good conductor or not? That
Lost
is
and
the loss tangent. Exactly. So, always remember loss tangent is sigma by omega epsilon. If that is very, very greater than 1, we say it's a good conductor. So, uh, so we are looking at the range of EM spectrum. That means we are looking at the frequency. For what frequency copper becomes a good conductor? That is a basic question. So let me rewrite this. So omega very very less than sigma by epsilon. What is omega? 2 pi f. So 2 pi f very very less than sigma by epsilon, or f very very less than sigma value is given to you 5.8 into 10 power 7 by 2 pi into epsilon value is epsilon naught. So let me write it 1 by 36 pi into 10 power minus 9. Okay. So if you solve this, you will get frequency less than 1 approximately. So this calculation if you do, you will get it like frequency less than 1 into 10 power 80 hertz. Now, what is the understanding? If the frequency is less than this number, that means 10 power 18 hertz, approximately 10 power 18 hertz, then the copper is a good conductor. Okay, so this range is basically X-ray range. Okay, IR visible UV. So that is the question asked here. So visible, all of you know that it is 400 to 700 nanometers. This is wavelength. If you know the wavelength, you can calculate the frequency. Similarly, UV and IR also you can calculate. So all these, so visible will come approximately 10 power 13 hertz. UV will be approximately 10 power 15 hertz, and IR will be like 10 power 16 hertz. You see, all these are uh, less than this frequency. So for all these frequencies, copper is going to be a good conductor. Okay, so that answers the question here. So copper is a good conductor for visible, UV and IR ranges. Hope this is clear.
Yes, ma'am.
Okay, so that's all I got for today's session. This I'll discuss in the next week with some more understanding in the week 7 content.
Okay.
Okay. If you have any particular questions, you can tell me, or we'll just end the session.
Yes, ma'am. I'll contact you through email.
Okay, okay. So, any particular doubts, you can just let me know so that I'll try to include that in the upcoming session.
Yes, ma'am.
Okay.
Thank you, ma'am.
Thank you.